Extreme physics.
All right, let's solve some circuit problems. Let's take a look at some of those homework problems I had. Problem number one, circuit. In our circuit problems, we had a 110 volt supply, and we had 3 resistors like this, and then we had voltmeters connected. This was 1, this was 2, this was 3. And this is a series circuit. The way that I've drawn it's probably pretty clear that it's a series circuit. There's only one path. But when you see the way they drew it, they've got like this, and it looks like there are multiple paths going around here because we have these devices. Like that. We had our voltmeters. Put a V there. And so it looks like there's multiple paths because you could imagine charge going around, and it would have a choice at this point. There's a junction right there, and it could go this way or this way. But if you remember the characteristics of an ideal voltmeter, this has infinite resistance, and so does this, and so does this. So effectively, electrically, this is what it looks like. We just happen to know the voltage across it because we have meters. Electrically, it looks like this. There is no current path through the voltmeter. Now, in real voltmeters, of course, there is some current that goes through it, but it's inconsequential if it's working properly, if it's a good voltmeter. So what's a voltmeter on V2? Let's see, what we had? We had right here we had a 20 volt drop, and here we had a 20 volt drop, and Kirchoff's voltage law, which is basically a restatement of conservation of energy, says that in any closed loop, the sum of the voltage gains has to equal the sum of the voltage drops. I see I have a voltage gain of 120 or 110, and I have a 20 volt drop and a 20 volt drop. 20 plus 20 is, I think, 39.8, and so we got 39.8 minus 110. Is that 70 volts? 70 volts, right? 70 volts. Let's see. 7, 8, 9, 10, 11. Yeah. Okay, so those add up. So V2 equals 70 volts. 70 volts is the potential difference across, I guess, resistor 2. All right, we had another series circuit here. We had, what do we have? We had a 20 volt gain, and then we had a couple voltage drop. What's the question? If the current through the 5 ohm resistor is 1 ampere, all right, so going through here we had I equals 1 ampere. What's the current through the 15 ohm resistor? Well, let me get my calculator out. I gotta figure this out. Let's see, 1 minus 0 times 1 plus that. 1! There's only one current path around here. So the current here is the same as the current that goes through this wire, is the same as the current goes through this, same as the current goes through this wire, and this wire, and this wire, and through the battery. There's only one path, so the current is the same everywhere. There can't be a buildup of charge. If there's a buildup of charge, you're going to get forces in the other direction. They're going to repel each other, and you're not going to be able to push them this way anymore, right? So the current is the same everywhere in a circuit. Otherwise, charges would build up, and that's not going to happen. You'd end up with a potential difference in the other direction. So the current through the 15 ohm resistor is I equals through the 15 is 1 ampere. All right. That was pretty straightforward as long as you understand that in a series circuit, the current has to be the same everywhere. We have a series circuit again. We have 3 resistors. We know 2 of the resistances. And there's an ammeter here reading 2 amps. And we got a 24 volt gain here. And let's see. This was R1 and R2. Well, we find the equivalent resistance of this circuit. and then we could figure that out that way. So here's our equivalent circuit. And it looks like this, our equivalent. Now, I don't know what that is, but I do know that we got 2 amps going. I don't know which way it's going. Let's say it's going this way. I know that we have 2 amps flowing in this circuit. So let's find our equivalent. Well, we know that R equivalent equals V through the equivalent over I. I through the equivalent circuit. All right. The voltage drop across that is going to be 24 volts. 24 volts divided by 2 amps is, what's that, 12? 12 ohms. So we got 12 ohms right here. This is 12 ohms. 12 ohms is that. All right. Well, these have to add up to 12 ohms then. And in a series circuit, it's kind of easy to find the equivalent resistance. I think I'll go over here. I neglect this side of the board often, and I think I showed a little love. So what was I figuring out? Oh yeah, our equivalent in a series circuit is just the sum of them, right? And you can look that up in your Regents reference table. Equals. All right. So I know what that is. I want to know what that is. All right. So R3 then equals our equivalent. Do a little algebra. R1 minus R2 is our equivalent. What did I say? 12 ohms. 12 ohms minus 4 ohms minus 6. Ooh, that's not a 6 at all. That looks like it was the beginnings of a 4. 12 minus 10, I think is 2. 2. R3 equals 2 ohms. All right. So 2 ohms. Does that make sense? Why don't we check this? Why don't we make sure our voltages work with that? That way we can work backwards, make sure everything's good, everything's solid. All right. So what's V1? V cross 1. V1 equals I1 R1. Equals 2 amps, because it's a series circuit. Current's the same everywhere in a series circuit. 2 amps times R1, which is 4 ohms, is 8 volts. All right. We had 8 volt drop there. Right there. How about V2? V2 equals I2. R2 equals 2 amps times R2, which is 6 ohms. Boom. 12 volts. 12 volts. All right. So far, so good. 12 plus 8 is 9, plus 3 plus quarter carried 3 is 9, and 4 is 2. And so that's 20 volts right there. And so this better be 4. Let's see what we got. Let's see. Is it 4? Let's see. I like it when the physics works. It's always a special time when the physics works. V3 equals I3. R3 equals 2 amps times 2 ohms, which is 3 carried to 4 plus 5 is 9, 4, 8 and 6 is 3. That looks like it is 4 volts. 4 volts. 4 volts. Let's see what do we got here. What do we have? We had 2. Yes! Yes, the physics work. It's good when physics works. They add up to 24. 8 and 12 and 4 is 24 volts. Golden. I'm confident in my answer. The resistance to R3, I believe, is 2 ohms. Right. Try another one.
Just keep it inside. Learn how to hide your feelings.
All right, we still recording good. Number 4, an electric circuit contains an operating heating element. All right, I'm going to, here's my heating element. It's a resistor. Right? It's a heating element. All right, so here's my resistor. Contains some sort of circuit with and a lit lamp, which statement best describes why the lamp remains lit when the heating element is removed from the circuit? All right, well, we got two possibilities here. Is this lamp connected in series or parallel? Let's look at both options and see which one is going to work out for us. All right, so we got a lamp, right? And let's start off. Here's my lamp. Oop, that's not a great lamp, but it's a lamp. And then we have some sort of voltage source right here, right? There's one way to do it. It's got a heating element, and we got a lamp. And then I guess the only other way to do it is, because we're going to plug this thing, we got our voltage source. These could be connected in parallel. Let's see, like this. You got that. There's my heating element. There's my heating element. There's my lamp. All right, now what happens? Which statement best explains why the lamp remains lit when the heating element is removed from the circuit? Well, let's do an experiment. I'm going to get my heating element remover right here, and I'm going to remove the heating element. And let's see if the lamp stays lit. I remove it. Is that lamp going to stay lit? I don't think it will, because there's no potential difference across it, right? We need a closed circuit for their potential difference. There is no potential difference across here. That lamp's not going to stay lit. It's going to go out. Right? It's going to alert you that the heating element was removed. How about this one? I'm going to remove the heating element like that. Will that lamp remain lit? I think it will. Because we got a path so the current can go. We got this voltage source pushing the charges out, and they can go through like this, right? In this case, we got something pushing the charges, but they have nowhere to go. They're going to build up here, and then they're going to start pushing back. You're not going to get any current flowing in this one. Not going to happen, right? We don't have a closed circuit. We got a potential difference, but not a closed circuit, so we're not going to get current flowing here. This one we will. We got our closed circuit. No current's going to flow there, but it's okay because the heating element's been removed by the heating element remover. All right, so let's see what the answer is. The lamp has less resistance than the heating element. Well, that's probably, I don't think that's the issue here. The lamp has more resistance than that. I don't think it has to do with the resistance of any of these things. Let's see what C is. The lamp and the heating element are connected. No, they're not. It's not like this. In fact, I'm going to put a big red X through it. It's not like that. Look at that. Multicolored. The lamp and the heating element are connected in parallel. Yes. Before I removed them, they were connected in parallel. Well, the answer is D. They're connected in parallel. Oh, this is 5 silly. It's silly. But let's draw a picture anyways. Connected in series. They're in series, one right after each other, right after the other. They're connected in series. If the current through the 4 ohm is 2 amps, what's the current through the 8 ohm? Well, it's also 2 amps. Now, I don't know what's going on in the rest of the circuit because they didn't say, but I know that if these are in series and this has 2 amps going through it, this is also going to have 2 amps through it. So the answer is 2 amps. A 10 ohm resistor and a 5 ohm resistor are connected as shown in the diagram. What kind of circuit is that? That looks like it's parallel to me. As you can see, the 10 ohm has a direct connection both sides to the battery. Same thing with the 5 ohm. And they're in parallel. They share a common potential difference. If the current through the 10 ohm is 1 ampere, all right, so we got 1 amp going through here. Oops, wrong way. Wrong way. Yeah, that's the wrong way. The current's going this way because this is the positive end of the battery and the negative. I'm coming around this way. So what do we got? 1 amp. All right. So the current's going. Keep in mind the charges, the electrons are flowing the other way, but current is the direction positive charges would move if they were moving, but they're not. But anyways, positive charges go like that. And all right, so we got 1 amp going through there. What is the current through the 5 ohm resistor? Well, they're not going to be the same, right? We got a bunch of guys going, like you can imagine a bunch of cars going all this way. Some of them are going to go this way, some of them are going to go that way. And it turns out more are going to go this way because it's easier to go that way. Electrons are like that, right? If it's easier to go, more of them are going to go that way. More of them are going to go this way because there's less resistance to the flow. So let's figure that out. If we only knew the voltage of this battery, we would be in good shape. And of course, we can know that because we know the current through that resistor, and we know it's connected across the battery, and we know the resistance. I'm going to call that R10, right? So we know that we can figure out the voltage across that, right? Okay, so V10 equals the current through 10 times the resistance of the 10. Now the resistance of the 10 is just 10 ohms. But anyways, so that's 1 amp times 10 ohms. And let me give it a well, I don't know what my calculator is. 4 plus 3 is 9, and 8 is 20. All right, okay, so that's 10 volts. All right, so there's 10 volts from here to here. So the voltage drop from there to there is 10 volts. Well, conveniently, the voltage drop from here to here is also the voltage drop across the 5 ohm, right? From here, they're both here. They share a common voltage. So anyways, so I can figure that out pretty easily. What do I want to figure out? What am I trying to figure out? The current. I5 equals V5 over R5. All right, V5 is 10 volts. And R5 is 5. 10 divided by 5 is 2 amperes. All right, so there's 2 amps going through the 5 ohm. I knew that ahead of time. I didn't have to figure it out. I could see it. If it had half the resistance, it's going to have twice the current. But anyways, there you go. So I guess the answer was 2 amps, 2 amperes. All right, got something like that. All right, we know the ammeter reading. We know the voltage across these. And what we got to realize is we're going to get some current going through here. I'll call it I bat, right? Now, some of that is going to go through here, right? And then the rest is going to go here, right? So these two added up equal that one, right? You got a bunch of cars coming into the intersection. The number of cars in the intersection better equal the number of cars out, unless they got a sinkhole where cars are disappearing or something like that. So same thing with charges. They're hunks of stuff, and you can't build them up. If they build up, they start pushing really hard. So we got current going in. Someone's going to go this way. Someone's going to go that way. So let's simplify the circuit. That's far too complicated for me. I think what I'm going to do is find our equivalent, right? Because if I just build an equivalent circuit that looks like this, it's got an ammeter, and it's got an equivalent resistance like that, our equivalent, and we still have 10 volts. And when I know, if I can figure out, if I knew that, I can figure out the current here. The current in here is going to be the same as the current there, right? It's going to go through the battery. I just need to figure out what is our equivalent. And in a parallel circuit, you can check your Regents reference table and see that our equivalent equals 1 over R1 plus 1 over R2. In this case, we got 2 resistors. So we're going to go 1 over, what did we say, 40 ohms? 40 ohms plus 1 over 40 ohms, right? Keep in mind when we do this in our calculator, we want to think of it this way. We want to use the x to the minus 1 key, right? So really we want to think about this as this is, so 1 over 40 is 40 to the minus 1, plus 1 over 40 is 40 to the minus 1. But we don't want these, we want 1 over that. So we're going to, after we add those up, we're going to invert that, and the whole thing, x to the minus 1. And I know that's going to be 20 ohms is going to be our equivalent resistance in this case. So, all right. So this is 20 ohms. So I equals V over R equals 10 volts divided by 20 ohms, I believe is half an amp. Half an amp. All right, we got half an amp. Yeah. All right, so the ammeter here, we got half an amp. Going right through there, through that ammeter. It's going this way. The current's going this way. Of course, the electrons are actually moving that way, but let's not tell anyone that. All right. Which two of the resistor ranges below have the same equivalent resistance? All right, well, let's see. We got two resistors in series, and in series, they just add up. So our equivalent equals 1 ohm plus 1 ohm, which is 2 ohms. All right, so A is 2 ohms. So our equivalent equals 1 over R1 plus 1 over R2 equals 8 ohms to the negative 1 plus 8 ohms to the negative 1 to the negative 1 is 4 ohms. So that one's 4 ohms. 4 ohms is the equivalent there. So, all right. So 8 and we got 4 and 2. I don't think they're the same. I'll check that in my calculator, but I don't think they're the same. And so our equivalent equals R1 plus R2 equals 2 ohms plus 2 ohms, which is 4 ohms, which is remarkably close to 4 ohms. So these look awfully close. So they're parallel. So our equivalent equals 1 over R1 plus 1 over R2 equals 2 ohms to the minus 1 plus 2 ohms to the minus 1, all to the minus 1, which is 1 ohm. All right. So from, I think 1 ohm and 4 ohm are the same. So I guess the answer is C and D. No, it's not at all. These are 4 ohms and 4 ohms. So the answer is B and C. B and C. There's our answer. B and C have the same equivalent resistance of 4 ohms. A physics student. This sounds suspicious. I wonder if the problem would change if it was like a biology student. Let's dig further. A physics student is given 3 12-ohm resistors with instructions to create the circuit that would have the lowest possible resistance. The correct circuit would be all right, well, if you want to go low resistance, you slap resistors in parallel. Because every time you slap a resistor in parallel, it lowers the equivalent resistance because you give the circuit another path to travel. So, if I want the lowest equivalent resistance, I'm going to put them in parallel. Let's draw that. I'm going to play the part of the physics student. Physics student given 3 resistors. All right, so here's my 3 resistors. I'm going to put them in parallel, right there, because I give myself more paths to go. Oh, that's not very good at all. To go on. So that is going to be the lowest resistance. Every time you add another path, you make it easier for current to flow through this thing. So they're all 12 ohms. 12 and 12 and 12. All right, we got 3 and then. The correct circuit would be a series. No, not series. B is series. No, not series. C, parallel circuit with equivalent resistance of 36. This isn't going to be 36. It's going to be smaller than the smallest. It's got to be less than 12. I guess the answer is D, 4 ohms. Let's make sure this works out to 4 ohms. Let's see. Our equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3 is 12 ohms to the minus 1 plus 12 ohms to the minus 1 plus 12 ohms to the minus 1, all to the minus 1. La 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 la. That'd be 3/12. You add those up, that'd be 3/12. So this is 12 thirds. So this is gonna be 12 thirds, which I believe ohms is 4 ohms. 4 ohms. The answer is D. Yeah, that was right. Okay, D. D. D is the answer for that one. Let's see. If a 15 ohm is connected in parallel with 30 ohm, what's equivalent resistance? Well, it's going to be less than 15. That's for sure. That's for sure. I don't even want to do that one. There's a simple way to make sure you got your current right at a junction. It doesn't matter how big the junction is. It doesn't matter what's happening in the circuit on the other side. As long as you know the current in all the branches except one, you can figure out what the other one is. So let's say I had a junction like this. I had a wire and I don't know. So we got something like that. Let's add another wire. We got something like that. And let's say we had, I don't know, 10 amps going in. And so we don't know what's going on in the rest of the circuit. It doesn't really matter because we can figure it out anyways. And then I had 3 amps and then 2 amps and I don't know. And let's go with 1 amp. All right, so we had that. And the question is, if I had an ammeter here, what's that going to tell me? What's that going to tell me? So, an easy way to do it is the current into a junction, this is a junction where they all come together, has to equal the current out. You can imagine cars going in, all the numbers of cars that go into an intersection. If you notice, the same number come out eventually. What I would do is, let's just make a chart. And I'm going to make, here's the in and out. So this describes the current at the junction. In and out. Right, there's their in and out. All right, and then I'm going to methodically, I'll start here and go around the loop and figure out what that must be for them to be balanced. All right, so 1 amp, is that into the junction or out? Well, there's a junction, it's in. 1 amp in. All right. 10 amps, is that in or out? That's in. All right. 3 amps. This is looking like it's going to be out. 3 amps, is that in? That's in. Boom. 2 amps. That's out of the junction. That's going away. That's 2 amps out. All right. They got to be balanced. They're not balanced yet. So we definitely have current in this one. Must. Let's see what these add up to. So this one is 14 amps, and that's 2. But this has to add up to 14. So it looks like we must have 12 amps here, right? That will add up to 14 amps, like that. Those will add up to 14 amps. So this one must be 12 amps out, right? So we must have 12 amps going that way, out of the junction. So that's how you do it. The current into the junction has to equal current out. Give yourself a nice little chart if you're having a problem with this. Figure out what's going in, figure out what's going out, and then what you have to do something to one of the sides to balance them. In this case, I needed to I need to mess with the outside to get them to balance. So there we go. Right? Beauty. All right. Hopefully that helped out a little bit. I'll be back soon with more. See ya.
Extreme Further.